So in this session, we will see how we divide our radio frequency up into different bands and different channels. And so the goal of wireless communication is to really get a hand on the different frequencies that are in use for wireless communication. So that's what bands and channels is about. But before going to bands and channels, channels and bands, so we will just get closed the open concept that we have, that is antenna. So we have almost covered everything that is required for the antenna section. So few parts are pending, so that we will cover, and then we'll start the channels and bands. So in yesterday's session, we have understood the different accessories that are there for the antenna and different types of antenna, different accessories that are involved in the antennas. And then we have seen that the antenna provides the passive gain, and also the cables in the specifically in the outdoor antennas, the cables that are present, so that provides some attenuation. So that is in dBs. So if particular cable is supporting some frequency like 50 megahertz or 150 megahertz, the attenuation for every 100 feet of such cable is like 1.5 dB of attenuation we get on that cable. So basically the transmitter is going to generate the AC signal, and it is transmitting on these cables. And these cables are going to attenuate the signal up to 1.5 dB. Okay. We know how much 1.5 dB is mean milliwatts, because dB is a comparative measurement, whereas the milliwatt or the watt is the exact unit of measurement of power. And not only this, it will add few other attenuations like the lightning arresters, then few other components that we studied in yesterday's session, like lightning arresters are there, then grounding wires. So those all things are going to add to the attenuation. And the total power at the end of the antenna, that is antenna is about to radiate the signal out into the environment, so that particular point is called as EIRP, equivalent isotropic indicator, power indicator, right? EIRP, radiation power. So there are different kinds of antennas that are available in the market, but choosing an antenna is very difficult task, as you have to be very familiar with the charts and the kind of radiation that are going to emit. So different environments need different antennas. Suppose if it is an outdoor antenna, then you need point-to-point antennas like this Yagi antenna or the patch antenna. And if you want highly directional antennas, we have parabolic dish antennas, grid antennas. So in our offices and all, we use normally the omnidirectional antennas that are installed inside the AP. Okay, we will not be able to see it. Suppose if you want to have a better antenna, so you can use external antenna as well. In Cisco's AP, you will get two kinds of antenna, that is internal antenna and external antenna. So whenever you are referring to an antenna, so it is like I, that is internal, and E, that is external antenna. This one here, it is a monopole antenna, and its radiation pattern you can see, but this one is for omnidirectional. So this is how the radiation pattern, azimuth pattern is nothing but when you look from the top. Elevation pattern is something when you look from the side. And I have told you how to calculate these values of dB. Okay. I hope that part is clear. So this is the directional antenna. This one is grid antenna used in outdoor environments. Sector antennas are like mobile towers. And then we have cables, connectors, amplifiers, lightning arresters, grounding rods, and all. So these are all the accessories for the outdoor antenna. So before going to the line of sight and Fresnel zone, let me share with you the data sheet of the antennas, Cisco particularly. So this is a Cisco Catalyst 9130 access point. Okay, this is the latest model 9000 series. In that it is 9130. And here we can check out the antennas that it has got. So these are all the brackets to mount the access point. So as you know, these are inverted and put on the top of the floor, right? These kind of access points, lightweight access points. So here you can see the inside picture of the AP. Okay, this is the Cisco radio frequency ASIC. Okay, this is a custom RF ASIC, software defined radio using a mini PCA slot. So this is nothing but a 2.4 gigahertz radio, 5 gigahertz radio, and here is the antenna. Okay, so very small antenna. Not you will not be able to check out, but I will try to zoom. So it is kind of a patch antenna. You can see 1, 2, 3, 4, and 5. The first one is RF ASIC antenna for 2.4 gigahertz and 5 gigahertz. It provides 4.5 dBi of gain and 5 dBi of gain. And you can see there is IoT antenna which provide 2.5 dBi of gain. And there is micro antenna and dual band macro antenna which provides 4 and 5 dBi gain. So higher the frequency, the gain is more, as you can see. Okay. And these are the antennas that are present inside the access point. Okay. And there is one more thing that is called radio for 2.4 and 5 gigahertz. So what is a radio? We'll learn later, radio or radios. So here you can see the pattern of um, the radiation that it will generate. So this is how exactly it will look. Okay. So 5 gigahertz microcell. So it looks like this. You have inverted downwards. So it will be like this. And here is the azimuth chart. When you look from top, so it looks like this. When you look from side, so the radiation looks like this. So this is the radiation pattern that you can see for these particular antennas. Okay, by looking at the radiation pattern, so can anyone tell what kind of antenna it is? Omni, yeah. Omnidirectional antennas. It is a omnidirectional antenna. As you can see the radiation pattern over here. So it is omnidirection. Yeah. So this is the radiation pattern you can check out. These are the cables if you want to have an external antenna, right? So this is what we talked about. This is the internal antenna that is in the box itself. Inside it is kind of a patch. Then here, if you want the external antenna to be connected, so you can use these cables, antenna cables, and then you can have the dart connector. As we saw in the previous session, you can have a dart connector. So radios we will see later. But this is the antennas that we are having inside the access point. So if you provide the external antenna, so obviously the coverage will be more. Okay, the coverage of the antenna will be more. Suppose the coverage of the antenna is like 1 feet. When you use a monopole antenna, then you want to have more coverage, then you use a different antenna, or you can add up the antennas, more antennas as well. So you can have dart antenna as well, so that you can have more coverage. And one important aspect, as you know, if you increase the power, so it can increase the range of the antenna as well. That means in feet. So exactly, to be precise, like how much feet? Yeah. Um, so there is a chart for it. I will just share. I think it's not here. I will share the chart with you. Okay. So you will understand, like each antenna, how many feet it can do. And also, when you one thing is increasing the power. So if you increase the power by 6 dB, so half the length it will increase. The distance will increase by half, like 1 feet. So if you increase the power by 6 dB, it will be 2 feet. In the opposite direction, if it is like 2 feet, you want to decrease the distance, you will make it as 1 feet. And as I have said, it is a two-way communication. When the antenna is sending the signal to the client also has to send it back, right? So that is also one factor that you need to consider. Okay, so let's go back to the. So here you can see the antennas, external antennas that are connected like this. And normally the APs will be mounted on the top of the ceiling. And if you are connecting external antennas, you need to make sure that attenuation is same across the cables and the connectors and all. So the impedance should match. So why the impedance should match, I will explain that later. Okay. So 2 cross 4 cross, it will come in MIMO. Okay, we will learn in MIMO. 4 cross 4 antenna, 8 cross 8 antenna, 4 transmission, 4 reception. So that's what 4 cross 4 means. So that we will learn in MIMO. Okay, that is next session. So you can see this is how the access point will be mounted, and it is inverted downwards. There's some recommendation for this. Okay, I will share this document link in the monday.com, so you can check it out from there. Can we install in wall rather than ceiling? Wall. Yes, you can install wherever you want, but the orientation of the antenna really matters. So when you purchase the antenna, so you need to check out how the orientation is. If it is a semi-directional antenna, so then it will send the radiation in a particular direction, right? So according to that, you need to place the AP. So that you need to check the orientation of the antenna, and looking at the data sheet, you need to understand where it is, how it is oriented. So that is important. And also the charts that you are seeing here, right? Azimuth chart and all. So if you see the azimuth chart here that we just saw, see, if you keep it like this, inverted, so it is going to normally cater in one direction like this, semi-directional. So whatever is in the backside, this lobe particularly, it is very less. Okay, this is a elevation. Elevation is nothing but when you're looking from side. So as you can see, when you are keeping the AP like this, so antenna is on the top, so it is going to send the signal in a unidirection, right? Like this. So we say unidirection, but or the semi direction. But if here also some part of radiation will be there, because when you stick a hand into the pond, so it is going to create ripples, but you are restricting it, but still um, some signal will be going in the other direction as well, but that is very not so strong. So this is a semi-directional antennas pattern. Okay, you can see in a single direction it is going. So according to this, you need to plan and you need to install the antennas. Okay, so yeah. Let me switch the tabs and go back to the PPT. Is visual line of sight. So line of sight is an imaginary line between an observer and the target in communication. So that is nothing but in the outdoor communication, if you have 2 points and the point directly coming from point A to point B antenna, that's a transmitter and receiver, and suppose there is no obstruction in that path. So that's a clear line of sight is important to have high speed communication. So for every 7 kilometer, the earth is bulged. Okay. So we need to consider that also. If you take this picture over here, so this is the transmitter antenna, this is the receiver antenna. So this is the line of sight. As there is no interference between these two, transmitter and receiver, the communication will be very good, because the line of sight is intact. Okay, so the line of sight is nothing but the imaginary line between an observer and the target. In a communication, line of sight is the direct path from transmitter to the receiver. It is important for the high speed communication. Line of sight is a vital factor in wireless communication. Some forms of wireless transmission are completely blocked if anything comes between the transmitter and the receiver. Most wireless transmission uses radio waves, that we already know. The Fresnel zone is an imaginary elongated football shaped area that surrounds the path of visual line of sight between two point to point antennas. So what's a Fresnel zone? So when you are sending the radiation from point A to point B in an open space, when you are sending the radiation, we know that it goes all the direction. Either it can go vertically or else it can go horizontally, depending on the orientation of the antenna. And now, when you are sending the radiation, so the radiation is not a smoke, right? A smoke is generated in the environment. So it is not similar to that. So we can imagine the radiation similar to when you fill the air into the balloon, right? So it has some structural integrity. Similarly, when you let the radiation out of the antenna, so it has some structural integrity. Structural integrity will be maintained when you have the line of sight properly, like between the transmitter and the receiver, the line of sight is intact. Suppose if there is any if there is any tree that is coming in between, okay, and also some buildings are coming in between, and some portion of your signal is lost here, right? So at that time, the structural integrity of the radiation that you have sent is little bit it is a little bit compromised there. The signal is compromised and the structural integrity is not that good. So we can say that the signal is not good, because as a signal as a whole, the radiation as a whole, it has some parts missing. But still, the antenna will able to understand in case if it is hitting the right aperture that is configured. So there is something called as RSSI, one thing, right? And also the signal has to hit the right aperture of the antenna. So then only the signal will be understood as a ones and zeros. Okay. If some portion, if 100% of the radiation is received at the end receiver, so then it's a very good signal. But ideally, that's not possible. Okay. Either because of the free space path loss or through some interference like this. So some part of the radiation will be gone. So in that case, but some part of it is remaining. So if it is like 50 to 60%, then the antenna that is here will be able to make out whether it's a 1 or a 0. So they will be able to encode the signal, and then again they will reconstruct and send it down to the receiver side. So Fresnel zone is an imaginary path where when you are sending the signal, so there is we know that when the radiation goes out, it is not bounded in a medium, right? Like this exactly, but it can go little bit high also, down also. So that is what Fresnel zone is. But when you send that radiation, it has got structural integrity when it gets hit by some object. So the Fresnel zones are imaginary line. We cannot say it is like this much distance only or this much distance only. So depending on the power that you provide and the environment, it is going to send the radiation from point A to point B. But some part of the radiation is hit by some obstacle. So that structural integrity will be little bit affected, and then the signal strength will decrease. Once the signal strength decrease, so it will be the receiver sensitivity should be good to understand the signal if it is a 0 or a 1. Okay, so that is what Fresnel zone is. Fresnel zone, you can have any n number of Fresnel zones, but it depends on all the radiation that you are sending. There is an infinite number of Fresnel zones that surround the visual line of sight. If the first Fresnel zone becomes even partly obstructed, the obstruction will negatively influence the integrity of the RF communication. Even an obstruction of less than 40% is likely to impair the performance of the link. To determine whether an obstacle is encroaching into Fresnel zone, you need to be familiar with a few formulas if you are willing to allow the obstruction to encroach 40% into Fresnel zone. Okay, so that's about the theory, but I hope you got the concept what is Fresnel zone in the outdoor Wi-Fi communication. And next is the signal to noise ratio. Okay, signal to noise ratio. So what is signal to noise ratio? Let's see that. So signal SNR is the difference in decibels between the received signal and the background noise level, not actually a ratio. Okay. So SNR is the ratio of the received signal strength to the background noise level. So when you send a signal, the legitimate signal also you're sending it through the antenna. Okay. When you send a signal through an antenna, if a legitimate signal that you are sending, so it is like minus 50 dB here. When it reaches at this point, it is minus 70 dB. Maybe it goes little bit further, then it is minus 120 dB. So this is kind of a noise. Okay, that is the signal will not be able to understood by the most of the receivers because it is a very small signal. It's a very small signal, minus 120 dB, and eventually it will be a noise in the network. Okay, so basically when you send a signal, it is two things. Either it's a good signal or a bad signal. So in bad signal, it's a noise. That means it still exists in the environment and it is not completely fade away. Okay, it is still in the environment and it has got the same frequency as the legitimate one. Or else the SNR can be caused by the natural phenomena as well. Okay, natural phenomena also the SNR can be generated. For example, like any uh, any machine that is radiating some energy, or the sun, throwing some rays on the metal and it generates some radiation and it has got the same frequency as the one that you are generating it manually. So that time it can intercept that signal. If the frequency is same, then the signals will collide. Okay, when the frequency is same and the signals will collide, and if there is a phase difference, either it can cancel the signal or increase the signal. So that's the concept. So when you are sending the radiation, if that noise is present with the same frequency, then some part of your signal will be taken by the noise. So only few part of the signal will be intact. Okay, like this is having the same frequency but different phase, so it is going to subtract the signal from noise. So that difference is called as signal to noise ratio. If a radio receives a signal of minus 85 dBm and the noise floor is measured at minus 100 dBm, so that is nothing but minus 85 minus 100 dB. So this becomes minus 85 plus 100, that is 15 dB. So this is the SNR. 15 dB is the SNR. The actual signal, legitimate signal minus the noise. Okay. The difference should be 25 dB. So this is the recommended SNR. Anything above 25 dB and above is considered to be a good SNR. If it is below 25 dB, so then the SNR is not good. So at the receiver side, you will not be able to make which one is noise and which one is signal. You will not be able to segregate it. So here you can see in the picture, so this is the legitimate signal that is going, and the noise floor you can see. So maybe the signal is like minus 62 dBm, but the noise floor is like minus 10 dB. So minus 62 plus 10, that is 52 dB. So this is a very, very good SNR value. Okay, the actual signal minus the noise floor is the SNR. Anything above 25 is considered as a better SNR. And in the real time, you can see this is a combination of legitimate signal plus the noise. Okay, this is how it looks. When you segregate it, you can see the signal and the noise. So data transmissions can become corrupt with a very low SNR. If the amplitude of the noise floor is too close to the amplitude of the received signal, an SNR of 25 dB or greater is considered to be a good signal quality. So next concept is antenna diversity. So let's understand. So till now what we have understood, Fresnel zone, line of sight, then we have understood what is SNR. Okay. So we have understood what is SNR. So antenna diversity. Wireless networks, especially indoor networks, are prone to multipath signals. So understanding antenna diversity, we need to understand what is multipathing. For example, you have an antenna and that particular antenna is going to send the radiation. But this particular signal gets hit by some object, okay, and then it starts generating the signal. I mean, it's not generating, it will also deflect or reflect, and then it is going to send the signal. And now that signal and this one is going to arrive at the receiver end. Okay. So when it arrives at the receiver end, this signal and this signal, so both have the same information, but the phase difference is there. So why the phase difference is there? We know the concept of phase. It is the comparison of two. Oh, sorry, I think it is. So we are learning a concept called multipathing. So we know that the radiation, when it goes out of the antenna, it is going in all the direction or in a particular direction if you're using the semi-directional antenna. While going, it interfaces with a metal object, and that particular radiation, when it gets hit by the metal object, it is going to reflect the main signal that was going, and a few part of it gets hit to a metal, and that is also getting reflected, and that reaches to the receiver antenna. So now two signals, same frequency, but the phase is different. Why the phase is different and what is the concept of phase? We know phase. Phase is nothing but if a signal is starting at time t, t1, and another signal starts at time t2. But it will have the same frequency. When you have the same frequency, the signals will collide, right? So that's the concept. The signal will interfere with each other. They collide if the frequency is same but the phase is different. Okay, either they can collide, they will collide, and either they can construct or destruct. Okay, so together. So that's what the concept is. When you send the radiation from the transmitter and that radiation gets hit by some metal object or any other thing, material, so it is going to reflect the signal. The main signal also is passing and it is going to reach the receiver antenna. When both the signals are received, so it will check whichever is having the good dB value. Suppose one signal is received at minus 60 dBm, another signal is received at minus 68 dBm. So this one it will choose because it is having the best signal. So that's what is called as the antenna diversity, and also that is receiver diversity. And transmit diversity is when it received the signal at minus 60 dBm, minus 60 dBm. Okay, so that's the receiver diversity. But before going to that, let's see this. Wireless networks, especially indoor networks, are prone to multipath signals. To help compensate for the effects of multipath, antenna diversity, also called as spatial diversity. Okay, so if you have seen the access point, we are going to use two antennas normally. Okay, so now because of the multipathing, so what is the effect of multipathing? So because of reflection, refraction, diffraction, or any other concept of the attenuation, you get the same information from two places. You get same information, but from two places you are getting the information because one wave is got reflected. Once it gets reflected, the main wave also is coming, and also the reflected wave is also coming. When they hit the antenna, so it can hit to two of the antennas. So whichever antenna is closer to that particular radiation, it will have the good signal strength. That is, suppose this antenna is detecting this signal at minus 62 dBm, and another antenna is receiving the signal at minus 58 dBm. So this will choose this antenna and this signal where it is getting the better power signal. So that is going to choose, and from that it will interpret the signal. So that is called the receiver diversity. Receiver diversity, and transmit diversity is from whichever antenna has received the best signal. So it will use that particular signal to send it will use that antenna to send the signal back. Okay, that is what transmitter diversity is. So just to summarize, in our normal access points, we use two antennas. One antenna will be used to receive the signal at a time. As we know that the wireless communication is half duplex communication, where only one client or one server can talk at a time. When you receive multiple signals because of the multipathing that is caused by reflection or diffraction or scattering, so you are going to get multiple signals. And once you receive the signals on the antenna, both the antennas will receive the signal, and whichever has received the better signal in terms of the decibels, it is going to consider that signal and it will start interpreting. So now when you want to send the signal back, so it will use that particular antenna on which it received the better signal. So that is called as the transmit diversity. The receiver diversity is the effects of multipathing will be used for our benefit because it will receive the multipathing signal. Suppose if you have a single antenna, so only one signal can be received at a time. Since you have two antennas that is spaced at a distance, right? That is spaced at a distance. So this is the distance. Suppose say distance is d. So because of this spatial diversity or spatial spacing of antennas, so this might have antenna 1 might have received the better signal, and antenna 2 has little bit lower strength signal. So this antenna will use this signal, and this signal will be interpreted instead of this signal that is received on antenna, suppose say A and B. So now while sending the signal back, so antenna B will be used to send the signal. Okay, because it has received the better signal. So that's what the transmit diversity means. And receive diversity, basically the signal can be received on two antennas. So that's what the receive diversity is. When the access point senses the RF signal, it compares the signal that it is received on both the antennas and uses whichever antenna has the higher signal strength. The AP will use one antenna as long as the signal is above a predefined signal level. If the signal degrades below the acceptable level, then the AP will use the signal received on other antenna. And what are the effects of multipathing? And what is the reason for generating multipathing? So because of the multipathing, data corruption can happen, signal nulling can happen, increased signal amplitude or decreased signal amplitude can happen because of the multipathing. And we have understood the idea behind the multipathing. Suppose when you are sending the radiation, so that radiation gets hit by the some obstacle, maybe a tree, building, or some metal body. It gets hit, and then it is going to reflect the signal. The main signal also traveling, but portion of it gets hit to a metal object. So that portion is again get reflected. But one thing to note here is the frequency remains the same of the reflected one and the main signal. See the characteristics of the wave. Like if it gets if it gets hit to an object, but still the frequency is same. But what is changing in this scenario? The phase is going to change, the amplitude is going to change, but the frequency remains the same. When you have two signals with the same frequency, they tend to collide and then tend to cancel each other or add or construct the signal. So the phase difference is very important. Suppose you have a minus 90-degree phase, sorry, 90-degree phase you are having. So then the signal will be constructed. I mean, it will be added. The signal strength, the amplitude will get added. If it is like 270 degrees compared to the main signal, then it gets cancelled out. Okay, the phase difference. Again, it depends on the amplitudes and how much it can cancel. Suppose the 50% of the radiation is intact after this collision will happen. So the receiver will be able to understand it. Okay. So that's what the concept of multipathing is. I hope this is clear. And the causes of multipathing: reflection, diffraction, scattering. So this we will learn in the attenuation time. Okay. So here is a picture for you to understand. You can see the ceiling when the signal is traveling, when it gets hit. So you can see it comes like this, and also the signal is going straight and the signal is going like this. So three radiations will go and hit here. Okay. So when you are imagining this multipathing, you need to imagine like you are blowing air into a balloon. And when you are blowing the air, few part of the air is going to hit a object and it is going to reflect back. And the middle part of it is just intact and it will go and reach the receiver. So similar to that concept, when the outer wave is going to hit the some object, it is going to again go like this, go like this, go like this. So when the receiver will receive it, he will think that is three signals. Okay, whichever is the better signal with better signal strength, so that is going to be considered. That's the receiver diversity. And you can see received signal, so it will be like this. Combined result, it will be like this. The reflected RF waves cause this condition to occur. The desired wave is combined with many reflected waves in the receiver. The reflected wave is also positionally different from the unreflected wave. See, positionally different. Okay, why they are telling positionally different? Because it has hit by an object and then it is reflected. Not all the radiation, but few part of the radiation gets reflected. So it has the same frequency as this one. And why it is like this? It is by design. Okay, that is the characteristics of the wave. So that's what we are going to learn, like how it behaves. Wave is not a kind of a smoke, right? You generate a smoke, you leave it in the environment, it goes everywhere. It has, but the radiation that you send, the RF signal, radio frequency signals that you send, it has got structural integrity. And when it gets hit by any object, either it can reflect, diffract, scattering can happen. Okay, the some part of the signal will be absorbed by the metal and some part will be reflected or scattered, depending on the depending on few factors that we'll discuss in the attenuation time. Okay. So there is a question. Fresnel zone is obstacle which is in between line of sight. Fresnel zone is obstacle which is between line of sight. So I will take this at the end, these questions. Please keep posting the questions so that I will answer it at the end. So you can see the next thing is multiple input, multiple output. But before going to MIMO, we will go to the band section. I hope you have understood the antenna concept. Okay. So you have asked few follow-up questions on this, like how we need to place the antennas, how far we need to keep them, and all those stuff. So I will just answer that, okay, in the later stage. But let's focus on today's topic and go to the next session. So I will take all the notes that you are sending, so I will answer them. So now let's focus on the channels and bands. Okay, another like 15 minutes we will focus on channels and bands. So basically we are going to divide our radio frequency into different bands and channels. Okay. And so the goal of wireless communication is really to get on different frequencies that are in use, like specifically for Wi-Fi communication, we use three different frequencies, that is nothing but 2.4 gigahertz, 5 gigahertz, and 6 gigahertz. And I am talking about bands, right? Bands. So what is a band? Band is nothing but the collection of channels. So what is a channel? Channel is a collection of frequencies. So band is a collection of channels. Channel is a collection of frequency. Okay. So why 2.4, 5, and 6? Only three bands? We know that when we talk about hertz, so it is frequency, right? Gigahertz. How many hertz is nothing but cycles per second, right? So gigahertz, 2.4 billion cycles per second. Just imagine the amount of information we can send in that particular 1 second. Okay. 5 gigahertz, more frequency. 6 gigahertz, more frequency. Now, we are not going to send a signal on a single frequency. Why? Because when I send a signal on particular 2.4 gigahertz, so in a wireless LAN environment, so there can be another 2.4 gigahertz signal, and then what happens is that is going to collide with this signal that you are going to send. So the other signal also can be a legitimate signal, but it is not concerned to you because it is coming from some other vendor's AP, or the company is like first floor, second floor, and in the second floor also you're using 2.4 gigahertz. So if you are using a single frequency 2.4 gigahertz, there is a high chance of getting collision. Okay, because it is on a single frequency. So what we do is, instead of sending this whole signal in a single frequency, I mix with multiple frequencies. So I will send for some time, I will send for some 2.4, that is nothing but 2401 frequency, okay, megahertz. 2402 I will send for some time. Okay. After some time I will send for 2403. So like this, I will send the signal on multiple frequencies I am going to send. I'm not sending it on a single frequency. When I send the signal, I'm sending it on multiple frequencies. And what is the objective of it? The objective is, suppose if because of the natural phenomena or any legitimate signal is also working on 2.4 gigahertz, but it is high likely that the it is going to have the same pattern. I am sending the signal for some time for 2401, then 2405, 2403, like this I am going to send on different frequencies. So the whole signal getting interfere, this whole signal will not get hit by the interference, because some portion of the signal might be lost, but other portion will be intact because I am not sending the signal on the same frequency. If I am sending the signal on the same frequency, then there is a high chance that the whole information get corrupted. But when I am sending the signal on different frequencies, a part of the information that you are sending gets corrupted, but that all can be compensated with other technologies that we are going to learn later. So that is why we are going to send the signals on different frequencies. So when I say 2.4 gigahertz, I am not going to send signal only on the 2.4 gigahertz single frequency, but multiple frequencies. So 2.4 architecture has concept 2.4 gigahertz band, or you can say spectrum. Spectrum is also nothing but a collection of frequencies. The band or the spectrum is collection of channels, and channels are collection of frequencies. So if you take 2.4 gigahertz, there are different frequencies in it. It starts from 2401. Okay, it goes till 2473 or 2483. All right, it can go from 2401, 2402, 2473. So 240203, like this. It can go up to 2473 or 2483. So basically this is 72 megahertz wide channel, 72 megahertz wide channel. So when I am talking about wide channel, so in a picture you might understand like this is a very wide channel and I'm sending the information on that. So it is that is not to be understood like that. So how it needs to be understood is, I can put more information when you have more bandwidth. So there is a difference between a bandwidth and a frequency, right? So what is the difference between a bandwidth and a frequency? Suppose you have a tap, and that tap is going to say a water gushing comes out like this, and with what force the water is coming out. So that is what frequency is. And the space of the tap or the width of the tap, so that is nothing but the bandwidth, right? That is what is the bandwidth. Okay, that is the bandwidth. So when we say bit rate is nothing but the total bandwidth. Total bandwidth. When we talk about throughput, throughput is nothing but how much actual water is going. The tap is wider, but how much it can send the water, so that is what at that particular time, so that is what the throughput is. But when you say bit rate is what is the total amount of bits it can send through that particular channel. But what we are talking here is the bandwidth. So bandwidth, so it is like 72 megahertz. When we say 72 megahertz, so it has a bigger bandwidth. So when I say bandwidth, what it exactly means is, I can put more frequencies on it. When I put more frequencies on it, I can send more information. Okay, there will be less distortion, less chances of retransmission. Because of that, the throughput will increase. Okay, are you following me? Okay. So we are studying about 2.4 gigahertz in the channels and band section. Okay. And in the 2.4 gigahertz space, now till now we have understood that it is not a single frequency that we are sending the radiation. When I generate the radiation, I am not going to send a single frequency from the transmitter and the receiver end. Okay, I'm not going to send us on a single frequency. I'm not going to send. Instead, I am going to use multiple frequencies so that the data that is lost because of the interference, it will lose a small portion of it instead of all the portion is lost. So that's why I am going to send the signal on multiple frequencies. In this process, we understood that 2.4 gigahertz is a band. So band is nothing but a collection of channels. Channels are nothing but a collection of frequencies. Okay. If you take 2.4 gigahertz, we have like 11 channels we have. In that, 3 are the non-overlapping channels. Okay, non-overlapping channels. And why it is and all, so we will see. And each channel is spaced at 22 megahertz wide. 22 megahertz wide, when I say what should come into your mind, that is the bandwidth. Bandwidth is nothing but the amount of data that you can send that particular time. Total bandwidth. So 22 megahertz is nothing but like you can use 2401, right? This is the starting point of 2.4 gigahertz. So you can go till 02, 03, 04. You need to add 22. So that is 2423. So from 2401 to 2423 frequencies you can use. That means 22 frequencies you can use. That is 22 megahertz. When you use 22 frequencies, you can put more information onto the your transmission. When you put more information, obviously you will have the speed of the communication will be more. The throughput will be more. The throughput will be more. So you have multiple frequencies, more throughput you will have. So that is 22 megahertz wide channel you are having. So in that 22 megahertz channel, it starts at 2401 and it ends at 2423. The center frequency is nothing but 2412. Okay, it comes 2412 is the center frequency. 2412 is the center frequency. So normally when we indicate the channel, we indicate it through the center frequency. This is the center frequency. Similarly, the next channel is spaced at 5 megahertz. So the another channel will start after 5 megahertz. That is, it is going to start at 2406. Okay, 2406. After 5 megahertz, one more channel will start, that is 2406 means the one more channel is 2411. So like this it will start and the sixth channel will start. Okay. So basically it will not overlap with any other channel. So these channels are getting overlapped. And what happens when the channels get overlapped? We know that when the frequencies will collide, similar frequencies will collide. So then either it can cancel or it can increase the signal strength. So if the signals are closely spaced means you are using frequencies almost similar. So then there is a chance of getting cancelled out. Okay. So how to avoid that and why this 6 megahertz sixth channel, channel 1, channel 6, channel 11. So these are called as non-overlapping channels. And these are the ones that we are going to use in our APs, access points. Why we cannot use channel 2, channel 3, channel 4, channel 5 for communication? Okay. And what about those frequencies, whether they will be used or not? Why only channel 1, channel 6, channel 11? So that we will see in the next session. Okay. So in a AP, how to define the layout, So those all things we will see in the next session as we are almost top of the hour. So we'll stop here. In tomorrow's session, we will complete 2.4 gigahertz, 5 gigahertz, and 6 gigahertz channel analysis. There are something called as unibands. Okay, unibands. We will learn about the DFS, okay, dynamic frequency selection, what that is, and different channels. And we will understand more analogy about the transmission of the radiation using these channels and how the communication happens on these channels. Okay, so this we will understand in the tomorrow's session. So don't miss tomorrow's session. We will cover many things about different 5 gigahertz, 6 gigahertz, and all. And we will learn about the channel bonding, that is important. Okay, then we will learn about the DFS and unibands, and those stuff we will complete it by tomorrow, 6 gigahertz band. Okay. So once this is completed, we will learn about MIMO. That is the Thursday's class, which is very important. MIMO is very important class. We will learn about MIMO in the on Thursday. Okay, then. Thank you for joining today's session. I hope it was you understood the concepts. And if any questions, please feel free to reach out to me. I can help you on WhatsApp or any other channel that you know. So yeah, we can continue from tomorrow.